next we have Naduvalath, who will be telling us about fundamental studies of ultracold collisions and reactions.
Well, thank you. It is a pleasure to be here, and always great to be back at ITAMP. And I would like to thank the organizers for inviting me to this meeting. So I'm here to give the probably the only chemistry talk at this meeting. And so I'll be talking about fundamental studies of ultracold collisions and reactions, basically to give an overview of some of the work in our group on quantum dynamics of cold and ultracold collisions. And I would like to acknowledge the funding agencies. So I'd like to start by giving a quick run-through overview of the key steps involved in quantum dynamics calculations of atomic and molecular processes. So there is the obviously the computations are done within the Born-Oppenheimer approximation for most of the molecular collision processes, and there are many well-established computational codes available for electronic structure calculations of the interaction potentials, Gaussian, Morpro games, or any of these program packages. Some of these are proprietary codes. And this part of the this part of the calculation is actually fairly well established in the sense many of these codes are proprietary codes and well developed. So it is user friendly. So many of them comes with lots of bells and whistles, and so unlike the collision dynamics, where most of the codes are developed in individual research groups by much smaller scale operations, so this is actually a much bigger scale operations. And once that process is completed, the interaction potential generally needs to be fitted to some usual functional form appropriate for dynamics calculations, and that has been also obviously a lot of efforts have gone on to that. But when you apply to cold molecules, ultracold collisions, the long-range potential needs to be described accurately, and that continues to be a challenging aspect. And so once you have this interaction potential, then obviously you can begin to do the nuclear dynamics for chosen initial rotational, vibrational, spin, hyperfine levels, and evaluate cross sections over a range of scattering energies. And for that, one may use classical trajectories, semi-classical or quantum methods, and obviously the complexity increases as you go down the list. And for ultra-cold collisions, one has to use the quantum approach. And so to do the quantum dynamics, obviously, if you want to do a full-fledged quantum dynamics, then you have the most obvious method is to use the quantum close coupling calculations, and that can yield a fully state-resolved product, rotational, vibrational, resolved reaction rate constants. But it is challenging for many systems of current experimental interest, and also including external field effects is difficult because that leads to proliferation in number of coupled channels. On the other hand, on the other end of the spectrum, one can use more simplified scheme, such as the multi-quantum defect models, in which the short-range interaction and coupling to the reactive channels are not explicitly taken into account, but external field effects could be included easily. And so these two approaches have become sort of the standard ways of treating cold collisions. But one may also consider a hybrid approach in which, say, in the short range, one could solve the full quantum close coupling, and in the long range, weld it to the quantum defect theory. And so it's kind of a few people, well, primarily at this point, we are looking at this aspect with the John Bourne, and there is one paper published from Jeremy Hudson's group on application of these techniques for inelastic scattering. And So this is not call from my mom, but it is the wireless. Okay. So I would. So with that as sort of an introduction, I would outline. This is a brief outline of my talk. I'll be talking about primarily about barrierless ultracold reactions using full quantum close coupling calculations. And we have applied to several systems in the past, but today I'll be talking about applications to O singularity plus H2, OH plus O, and some ongoing preliminary data on Li plus LIYB. Then I will talk about this hybrid close coupling MQDT approach applied to an inelastic non-reactive collisional system, but full dimensional rotational vibration transitions in H2H2 collisions. Now, before I go into the reactive calculations of the barrierless systems, I just want to spend a couple of minutes on some barrier reactions that we have calculated in the past, and there is continue to be some interest. So this is one of the benchmark systems in chemistry, the reaction of atomic fluorine with H2 and HD. So you have asymptotically F and H2 coming in here, and they form sort of a pre-reactive van der Waals complex, and the van der Waals complex can tunnel through this energy barrier for reaction and then end up in the product channels. Obviously, at room temperature or higher energies, the reaction will occur above the barrier, but at cold and ultra-cold temperatures, it will primarily occur through this tunneling mechanism. Now, we have looked at this process almost like 12 years ago when nobody was actually talking about ultra-cold reactions. And so using an available potential surface that time, we predicted the zero temperature limiting value of the reaction rate constant to be about on the order of 10 to the minus 12 cubic centimeter per second. And so this reaction has a large energy barrier, about 1.5 EV. And also because of the interest of this process in fluorine chemistry in interstellar medium, where HF is thought to be, the fluorine is thought to be mostly in the form of HF because the reaction is highly exergic and there are not many other destructive channels for the HF molecule. So the interest continues in the ultracold, in the astrophysical, astrochemistry area. But the reason I just thought I will mention this is because, so this was published in 2001, but earlier this year, about a month ago, this paper appeared in Nature Chemistry, in which new measurements of the rate constant of the F plus H2 reaction was reported at temperatures down to about 11 Kelvin. So all prior experimental data were at room temperature, and this measurement was at three data points. And obviously there are some uncertainties, and it also accompanied with two theoretical calculations by Millard Alexander. So this solid curve here is the theoretical calculation using a multi-surface approach in which the spin-orbit interaction in fluorine is included. So it required a non-adiabatic treatment. And then also a single surface calculation in which only the ground spin-orbit state of the fluorine atom is considered. And that is this dashed curve. And this is an earlier calculation some years ago by Acquilanti et al. Using a slightly different potential surface that has a slightly different long-range interaction and a slightly different barrier height for the reaction. This is fit to this high-temperature experimental data, and these are some rate constants that we have jointly with Alex and Roman Krems calculated for astrophysical application that used a slightly different potential surface. So again, what I try to illustrate here is that it is really hard to do experiments on this type of systems. And also, depending upon the type of potential surface that you use, because all these calculations, this one, and this one, all used a full quantum close coupling. So the difference is the difference in the interaction potential. So the interaction potential obviously is, computation of accurate interaction potential is still a very challenging issue, and it is particularly so for reactive systems. And this is one of our recent calculations on a system, helium C3 van der Waals complex. C3 is a linear carbon chain of interest in astrophysics. So this involved computation of potential surface for helium C3 interaction using what we believe is a very, very high level electronic structure method using the coupled cluster singles, doubles, and triples with the quadruple perturbative quadruple excitations. And what I want to show here is this black curve here. That is the full close coupling calculation using the actual potential that we computed. The uncertainty in the van der Waals region is less than 0.02 wave numbers, which is almost within 0.1% of the accuracy. So that means any higher order correction is only 0.1%. Then we scale the potential by plus or minus 0.5%, which is larger than the uncertainties in the potential, just to see how the results at the low temperature would change. But the red and green curve that shows the calculation using this scale potential yield almost exactly the same results, which means that for systems such as this is a closed shell system, you can evaluate potentials with sufficient accuracy that is appropriate for ultracold calculations. If you change the mass of the helium atom from helium-4 to helium-3, then there is quite a bit of sensitivity at low temperatures. But beyond 1 Kelvin, the mass difference or the small change in the interaction potential by this applying plus or minus 0.5% really doesn't seem to have much effect. So in certain scenarios, one may be able to compute very accurate potential surfaces that are appropriate for ultra-low energy calculations, but in other more complex reactive systems, it is still a challenging aspect. Now, to do quantum dynamics, the reactive scattering calculations, it is also complicated because unlike in non-reactive systems or in atom-atom collisions, you have the atom exchange occurring in reactive scattering. So one has to, so a single set of Jacobi coordinates, say, for atom A plus molecule BC, is not appropriate for reactive arrangements where you have AB plus C or you have AC plus B product channels. So one has to use a different set of coordinate system for reactive calculations, and usually the hyperspherical coordinates is quite widely used. So in this case, you have a single hyperradius that is appropriate for all three arrangement channels, and that is independent of the arrangement channel. So this is a schematic of the approach that we are using for the reactive calculations. We divide the hyperradius into two regions, an inner region, which includes the strong interaction region, and an outer region that is primarily the long-range part, and then divide each of these regions into a bunch of sectors, and then solve the close coupling equations from rho equal to 0 to sufficiently large value of rho, where the interaction potential is negligible, and do the asymptotic matching to evaluate the S matrix elements and cross sections and all those quantities. So the Hamiltonian in this coordinate system, it is quite well known. So you have the radial kinetic energy part, the interaction potential in the hyperspherical coordinates, and you have the angular momentum terms. And expand the total wave function in terms of this radial expansion coefficients and the angular functions, which are the hyperspherical surface functions, and the surface functions are obtained by solving the surface function part of the Schrodinger equation. And so that yields this set of close coupling equations for the radial motion, which are solved using standard techniques, except that I would like to emphasize the computation of the surface function itself is a time-consuming process. So for that has to be carried out for each value of the hyperradius. So we use an expansion in primitive functions in theta, which are Jacobi polynomials, and complex functions in phi. And these are some computational details, which is actually really not much important, except to say that the code is highly parallelizable, in theta and in omega blocks for the non-zero total angular momentum calculations and some other numerical details there. So, this is so we have applied this to the method is applicable at higher energies. At higher energies, obviously, you will have to include many angular momentum partial waves, so the calculations are obviously time consuming, but then you don't have to propagate to very large distances. But at low energies, you have to integrate the coupled equations to large separations, but then you don't have to consider higher partial waves. So there's always trade-off. But these are exploratory calculations. As I have indicated, the fluorine plus H2 reaction, even for that, there are in many low energy, very low temperature measurements of rate constants, and the same applies to O singlet plus H2. But it has been studied almost to death at higher temperatures in the chemical physics community. So we were just trying to see the overall behavior of barrierless chemical reactions at low energies. So in this case, we looked at the effect of vibration excitation of the H2 molecule on reactivity. So the three different curves corresponds to V equals 0, 1, and 2. The reactive, this is vibration conjugate from V equal to 1 and V equal to 2. And these are the elastic scattering rates. And this is basically cross-section multiplied by velocity plotted as a function of the collision energy in Kelvin. And so essentially what we see is there is no strong dependence of the rate constants on the initial vibrational level of the H2 molecule, which is essentially can be explained if you look at the adiabatic energies that are obtained from the surface function calculation. So this corresponds to the triatomic well, essentially the H2O molecule that is the intermediate that formed during this collision. And these asymptotically, these levels corresponds to various rotational vibrational levels of either the H2 or the OH molecule. And so I haven't labeled these levels because there are too many to label, but the H2 levels are somewhere around here. And so it doesn't really matter whether you use V equals 0 lowest vibrational level or V equal to 1 or V equal to 2. Once it is forming this triatomics complex, then it really independent of where you started from. So that is one way we explain the lack of dependence of the rate constants on H2 vibrational level. So when you do this kind of calculation, obviously you can start with the different initial vibrational levels of H2. You can get the reaction cross-section for producing OH molecules in different final vibrational levels as a function of the initial kinetic energy. If you want to look at the rotational distribution of the OH produced, you can again do it for different final vibrational levels. So in each of the final vibrational levels, you can look at the probability populations of different OH rotational levels. And so I just highlighted at two widely different energy regimes. If you look at the distribution here at low energies, it is, the final rotational distribution is dominated by one or two rotational levels. But here you would see a broader population of rotational levels. So essentially the reaction drives selectively certain final population of rotational levels at low energies compared to thermal energies. As I indicated, there are a lot of measurements at higher temperatures, and our calculations seem to reproduce quite well the experimental data. The predicted value of the zero temperature limiting rate constant, obviously no one is going to measure that for this reaction, is about, maybe somebody will, but at least for the time being. So it is seems to be about half of the value at room temperature, and again this shows the lack of initial vibrational level dependence of the rate constants. So so most of our work up to now have been applied to a simple system. Mostly, at least there is one hydrogen atom that was present, and there is obviously many of the experimental systems involve alkali metals or alkaline earth metals or other complex atoms, and so the number of coupled channels actually becomes really very large to apply on a routine basis. But anyway, so as part of our collaborative work, on the DOD Muri project. Svetlana Kotrachigova has computed potential surface for the Li plus LIYB system. And as many of you know, there is continuing experimental interest in creating fishback molecules of LIYB. And as far as I know, I don't know the latest on the experimental front. It is my understanding that the actual molecule, stable LIYB molecule, has not been created. But so we are just using this as an sort of an exploratory calculation to see if we can scale our approach to describe this type of systems, so that in the future we may be able to apply close coupling calculations to systems of this sort and more complex molecules. So you can already see from the plot of the adiabatic potentials that the number of coupled channels included here are a lot more. We have to, this is only the inner hyperradial region. We had to propagate actually to much larger separations. And here there are closely about 1,000 channels involved. So this is again for the LIYB plus Li leading to the singlet Li2 molecule. So this is this is not a spin polarized calculation. So we have so the singlet Li2 is quite deep, about 8,000 wave numbers or so. So there are many raw vibration levels. The LIYB V equals 0, J equals 0 has an energy somewhere around close here. So the LIYB initial state has an energy around here. So most of the channels in this case are the Li2, the product molecule, and the energy scale is with respect to the bottom of the Li2 potential. So 0 of energy corresponds to the bottom of Li2. And so in fact, it is this proliferation in number of channels that make these calculations really very hard if you want to do full quantum dynamics calculation. And this is without including spin or hyperfine or anything. And when you have to include those details, then it becomes almost impractical to do. So just to give you a comparison of the computational efforts, this is a basis set that we have adopted for the O plus OH calculations. If you recall, the surface functions are involved in expansion in basis functions with this index L max, L and M, which goes to L max and M max. So this is one basis set, and this is another basis set. This is the number of processors used in the computational surface functions, and this is average CPU time per sector, and it involves about 175 sectors here. So it takes about 10 days for this basis set and 14 days for this basis set to do the surface function part of the calculation alone. But that is not the time-consuming part. It is the coupled channel propagation that is the time-consuming part. And for O singlet plus H2, we could actually do it much quicker because that requires a smaller basis set. It's a more compact molecule. But if you look at Li plus LIYB, one requires a much bigger basis set. And with the same computer, same number of processors, we need almost 3 weeks to do the surface function calculation alone. That means this is just the calculation of the basis set that is involved in the close coupling expansion of the total wave function. So these are some preliminary data. So these sectors, the number of channels, number of steps in the log derivative propagator, the usual convergence studies that you do when you do these coupled channel calculations. So we just make sure that everything is converged with respect to various parameters. And this is energy in EV versus cross section in centimeter squared. And so it looks like one can use a less stringent convergence criteria at somewhat higher energies. But this level of convergence is quite appropriate for our purpose. We can actually split the calculations into two. We can actually, for even and odd symmetries corresponding to even and odd rotational levels of the product Li2 molecules, and this is some degeneracy associated with the even and odd case. So this is the cross section as a function of the collision energy. And this is rate constant. We basically multiplied the cross-section by the relative velocity. So what we find is fairly large rate constant on the order of 3 times 10 to the minus 10 cubic centimeter per second. And And so just a demonstration that we can actually look at systems of this sort, and but this is a preliminary data. It is not published yet. 5 minutes? Okay. So in the next 5 minutes or so, I would like to briefly outline some efforts that we are putting to see if we can combine the close coupling at short range and these long range theories based on the MQDT formalism at long range to simplify the process. And obviously, there have been a lot of work on MQDT by Gavo, Bohn, Paul Julian, and others. And the only work that we have seen is a recent paper by Jeremy Hudson and his group on Mg plus NH, in which he has combined the close coupling with MQDT. So we thought we would apply to, in fact, not a 3-body, a 4-body problem, H2H2, for which we have already done quite a bit of full close coupling calculations. So we have already close coupling calculations, the results of close coupling calculations. So we just decided to see if it will work. So anyway, the basic philosophy is you restrict your n by full coupled channel calculations in the short range, and then at some intermediate distance, you match your, say, the log derivative matrix from the coupled channel calculations to MQDT reference functions, and solve n1 channel problem instead of this n by n problem. And so this MQDT calculation is performed using a reference potential. And usually for atom-atom, obviously you use the long-range potential. But what we have found is that in molecule case, you have also the angular anisotropy. So the C6 alone is not a good description. But if you take the, say, spherically symmetric part of the interaction potential, that seems to be a better approximation for the long-range part. So, what we are looking at the collisions of two H2 molecules, which are free to rotate and vibrate, and then we are looking at transition between these rotational vibrational levels. These are diabatic potential curves as a function of the H2 distance, and so these asymptotically correlates with various rotational vibrational levels of the two H2 molecules. So these 4 numbers here are the 4 quantum numbers, V1, J1 of one H2 and V2, J2 of the other H2. So we are looking at some transitions that originate here, one H2 in 1, 2, 0, 0, V equal to 1, J equal to 2, other in V equal to 0, J equal to 0. There is one letter missing here, so that is 1, 0, 0, 2. And if you look at here, you see the coupling between these different states, different channels, that sees at about 10 atomic unit. So it looks like a 10 atomic unit or somewhere around that is a good point of matching between the short range full close coupling and the long range MQDT. And so this shows the elastic cross section for this particular initial states of the two H2 molecules. And for these, so what we have found in our prior work is that when you have initial combinations of H2 raw vibration levels like this, they go to some specific final rotational and vibrational levels, because the energy difference between these two transitions is actually quite small. So 1, 0, 0, 2 is this one, and 1, 2. So actually the difference is like 24 wave numbers, and so that makes the transition much more efficient. So again, anyway, what is shown here is the inelastic cross section as a function of collision energy. This is for a full close coupling calculation all the way, and these are from this hybrid approach in which the matching to MQDT functions are done at, say, 6.37, 8.5, or 9.2, and you can see the agreement at around 8.5 and 9.2 is pretty close to the full close coupling calculation. And one key thing to emphasize here is that the log derivative matrix from the full close coupling calculation at 1 microkelvin is used for all energies in the MQDT calculation. That means we have the short range, the log derivative matrix is computed at 1 energy, that is at 1 microkelvin, and the same log derivative matrix is used in all of the other energies in the MQDT calculation. So that actually is quite a bit of savings in terms of computational effort. So now this is for a different initial state. This is for ortho H2 collisions, and this is full close coupling. That is this curve here. Then you have the MQDT, in which the reference potential is taken as just a C6 potential. MQDT, in which we have taken the full potential is the spherical symmetric part of the potential. And you can see all those those two calculations, the red and the green, they cannot reproduce this the resonant enhancement in cross section here. But if you do and that is because the short range K matrix is calculated only at 1 energy. But if you do the calculation of the short range K matrix at a few energies and interpolate in between, then you can get a much better agreement with a full close coupling. And that is the case for the another initial state here, which corresponds to a collision involving ortho H2 and para H2. So in this case, there is a vibrational exchange. And again, full close coupling, the black curve, MQDT with just a C6 potential, or the spherical symmetric part of the potential. And again, in the first two cases, only the log derivative matrix is computed at 1 microkelvin. But in the blue case, that gives the best agreement with the full close coupling calculation. The log derivative matrix is computed at several different energies. So now I come to the conclusion part, which is essentially to say that ultracold chemistry is obviously gaining a lot of interest and providing opportunities for controlled studies of chemical reactions. And our effort has been trying to understand mechanistic details of chemical reactions at low energies, and obviously, with the long-term goal of controlling these. So for the quantum coherence, the reaction may be sort of the bad collisions, but from a chemist's point of view, if you want to see chemical reaction, then so one man's bad collision is another man's good collisions. And so MQDT seems to show some promise. Actually, it seems to work quite well for the H2H2 case. But applying to reactive system is still quite challenging, and so we are working on it. Finally, I would like to acknowledge my collaborators. Two UNLV postdocs, Gagan Pradhan and Jisha Hasra, are involved in the work. Jisha is involved in all of the MQDT calculations jointly with John Bourne at GILA, and Gagan Pradhan has been involved in the reactive scattering calculations. Beaufort and Phil Stansel are long-term collaborators and involved in the H2H2 work. And Svetlana is the one who actually computed the LIYB plus LI potential. And Brian Kendrick is a long-term collaborator on reactive scattering calculations. Thank you.
Any questions?
So in some of the calculations you reported, you mentioned that some non-adiabatic interactions were included in the molecular quantum effects, I think. Couple or something.
Well, the non-adiabatic calculation was on the fluorine plus H2 reaction. That it was not my work. It was the experimental paper that I highlighted. That was from Miller Alexander. That is, ideally one has to, because the fluorine has the P1/2 and P3/2 spin orbit states. Even though the reaction occurs through the P3/2 lower spin orbit state, there is some coupling with the excited spin orbit level. And if you include that, there is some small difference, but it is not a very significant effect for that reaction. But many chemical reactions involving open shell systems do involve non-adiabatic interactions, and ideally one has to take that into account.
So were these the non-adiabatic spin orbit, off-diagonal spin orbit coupling terms?
Yes.
Or something like that?
Yes, so that is what is involved in the fluorine plus H2 reaction, yes. Yes. We actually, before we tried for the Li plus Yb, we were trying to see if it would work, but the primary problem was that the available potential surface was really not very well behaved, and we couldn't get well converged adiabatic energies and the surface functions. So it was more like a numerical issue because the potential surface was really not behaving very well for the calculations. Yeah, it had some sort of singularities kind of thing, and so we had really tough time getting things converged. So it is again comes back to how accurately one can compute these potentials, because for modeling the experiments using MQDT probably works okay if you want to get the total some removal rate constant, because only the long range potential is used. But when you have to do the full close coupling, you need the full anisotropic potential surface, and if that is not if there are some pathological issues, then it is very difficult to get it converged in full quantum dynamics calculations. Sorry? Yeah, for barrier potentials, it is yes, because whenever you have deep potential, well, that is when it can support like hundreds or thousands of state, and it becomes much more time consuming and complicated. But barrier reactions are a lot easier to handle. Yes.
I had a question. Is there a sort of a rule of thumb for what the matching distance should be?
I think one way is obviously all the non-adiabatic coupling should be, or coupling between the different channels, I think they should cease. And so rule of thumb, like the H2H2 case, by looking at the potential curves, I think that was kind of a good indication. This would be a good point. If you have a strong coupling between various channels, which is always the case at short range, then you have to go beyond that. So obviously some numerical experimentation is required, but I think looking at the potential curves should actually help.
Okay, let's thank Paula again.